Hello everyone. In this video we are going to learn about a predictive model called decision trees and how to use them in Python. Now in the last lesson we introduced logistic regression as a predictive modeling technique for classification, and while logistic regression can serve as a low variance baseline or a fairly simple baseline model, other models can potentially yield better predictive performance. Decision trees are another relatively simple model that can be used for classification, but they can be grown to be quite complex and to potentially have more expressive power than a logistic regression does. Now, all a decision tree really is at its core is a series of yes or no questions based on some features or variables you have about the data you're working with that allow you to come to some sort of conclusion about whether a certain observation might belong to one class or another. For instance, with our Titanic disaster training dataset, we might ask a yes or no question in a decision tree like, is the person male or female? And if you say, yes, they are male, you'd make some decisions one way. And if you said, no, they're actually female, well, maybe you'd make different decisions for those cases. So to start off giving a basic example of a decision tree, we're going to use the Titanic disaster training dataset again and create that simple tree model that I just described using only the gender or sex variable to make the model. So there'll only be one decision point in this simple decision tree. To start off, we're just going to load the data in and process it. So for that, we're going to need NumPy and pandas. And then we're going to read in the data and pre-process a couple of the variables. You don't need to worry too much about what that's doing. We're just getting the data set. Now to actually make the tree model, we're going to use scikit-learn's decision tree model. So we'll show how to do that as well. From sklearn, we're going to import tree. That's going to give us access to the decision tree. We're also going to import pre-processing. We're going to have to pre-process any categorical variables we are going to use with the label encoder to make them numeric that the models can work with. So with these modules loaded, let's see how we can make the model. First, we're just going to initialize the label encoder to pre-process the variable we're going to use. So we're going to say label.encoder fit transform on the sex variable because that's the one we're going to use for prediction for this task. And then to actually make the decision tree model, all we have to do is take the tree module that we already loaded in from sklearn and then initialize a decision tree, so .decision tree classifier. That's what we're going to use in this case. Decision trees can also actually be used for regression problems when you're predicting real numbered values, but they can be used for classification as well. So in this case, we're going to use the classifier instead of a regressor. And after initializing our model here, we can just fit the model using our data and the target variable we're interested in. So after running this cell, we've now trained a decision tree classifier on that single variable. Now you notice the output of this cell here, decision tree classifier, shows various arguments that you can pass to the decision tree classifier that specify different aspects of how it's trained, such as max leafs in node, min impurity decrease, min samples in leaf. These are settings that govern exactly how the model is built. So they can affect things like how complicated the model is, how many observations are in each node, and that sort of thing. For instance, here we have max depth equals none. That means in this case we're building a decision tree that can potentially go unlimitedly deep, which might not be something we want to do if we're trying to build a model that isn't going to be overly complicated. But for now, we're not going to concern ourselves too much with all the different settings you can use here. This is something where if you're using decision trees in practice, you'll probably want to read through the documentation about what each of these different settings does and see what might be the best settings for your particular application. Right here, we're just going to use the default settings. Now that we've created this decision tree model, we can use the GraphViz library to render a visual representation of what the model actually looks like, the different decisions that were made, and the leaf nodes. So let's go ahead and show how we can do that. We're going to import GraphViz. we're going to say tree.export graph_viz. This is letting us export our model as a visual representation. So we're going to pass in our tree model. We're not going to have an out file because we're just saving this as a variable that we can graph. So then we say graph_viz.source. It's going to be the saved .data. And then we just call graph here, and this will render a little plot or visualization of what our tree actually looked like. So this output here is showing us that when our x0 variable, which in this case we only had one explanatory variable, it was gender, when that was less than or equal to 0.5, cases were routed in this direction. So when this was true, it filtered cases over here, and when it was false, it filtered those cases over here. And in this case, that meant that all 314 females were sent down this branch, and all 577 males were sent down this branch. And now if we were to make predictions using this model, the leaf nodes, so the one that contains all females and all males, would just predict whatever the most common outcome was within that node. Now to make predictions using our decision tree model, we can use the .predict function on our already trained model, or we can use .predictproba like we used last time with logistic regression to get the predicted probabilities instead of the predicted classes. So we're going to make predictions by taking our tree model. In this case, we're going to get the predicted probabilities with .predict_proba. We're just going to pass in the data, again, that we used to train it. That gets us our predictions. Now, from these predictions, I'm going to extract what the predicted probability of survival was for the female and males and just print those out. So that's what this code is doing. So I'll run that, and we can see that for females, the decision tree model is predicting that there is a 74.2% chance of survival, and for the males, it is 0.188. Now, what decision tree models are typically doing in the leaf nodes when they're coming up with these probabilities is simply calculating the ratio of cases that are true or not. So in this case, this number here, 74.2%, should be exactly the same as the overall survival rate of females because all of the females ended up in that same leaf node. And the same thing for males. So this 18.89%, this should be the same as the actual overall survival rate for males in this training data. Now let's add an additional predictor variable to our decision tree and rerun it to see how it changes the model. With decision trees, even adding one or two more variables can really change the structure of the model quite a bit and make it a lot more complicated. So let's see how that works. In this case, we're just going to add one new variable, the class variable called pClass, to our training data. So we're just making a new predictors data frame. Then we're going to rerun the tree model. We're just doing .fit again, but with the new predictors. So if we run that, we get a new decision tree classifier. And let's run our graph_viz visualization on it again to create a new graph. And we can see now that we have a model that's substantially more complicated than we did before. It actually has 3 levels now instead of 1. Before we only had 1 decision node and then 2 leaves. Now we have 3 levels with 6 leaves. It's actually so big we have to scroll over to see the whole thing. And we're making decisions now on multiple different variables. We can see that the root level decision is actually still the same as it was in the original model. It's asking for x0 less than or equal to 0.5 again. So that's the gender variable. So again, it's starting off by separating the passengers by gender at this first level. But then underneath that level, it's asking questions about the x1 variable. That's the second variable we included, the pClass. Now let's go down and make predictions again using this model. So to make predictions using this new tree model, we can use treemodel.predictproba again. These will get us the predicted probabilities. In this case, I'm going to make a cross tabulation that's going to actually show the death rates or non-survival rates based on both gender and class. So we'll run this, and given our predictions here, this is what the table output. And so this is showing us, for instance, that among first class female passengers, there were 94 of those, and their death probability was only about 3%. And for females in second class, there were 76 of those classified, and there were a death rate of about 7%. And interestingly, for females in third class, there were 144 of those, and the death rate was actually 50%. So much higher death rate for females if they were in the lowest class than the highest class. Now we're going to make one final decision tree model, adding in a couple more variables, just to give you a sense of how complicated decision trees can really get when you're adding in several different variables to train on. So we're going to add in the age variable and the fair variable, how much the person paid. And we're going to set a max tree depth this time when we train our model, because we don't want it to get too out of hand. You can easily make models be so deep that they're going to take a really long time to train, and we don't want to do that. So we're going to set this hyperparameter max depth to 8, which will limit our tree to being 8 deep. And we're just going to retrain the model using this new data set and this new max depth argument and make a visualization of it. And this is going to show you how crazy decision trees can get. With only 4 features still, we ended up with a model that, well, I'm going to have to zoom out to show you how big it is, but this model has a huge number of decision points here and tons of leaf nodes. So with the smaller models, it's possible to kind of work your way through it and actually kind of figure out what the model is actually doing in terms of it's separating by gender and then class and then asking a couple more questions. Once models start getting this big with this many decision points, it starts getting pretty hard to actually go through and try to interpret exactly what the model is doing, because it's just not feasible to look at all the decisions that are being made. But I just wanted to show you this to give you a sense of how complicated a decision tree can really get, even with only 4 variables. Now imagine a model where you had, say, 10 or even 100 different variables that you're working with, and you didn't set a max depth of 8, so this could be continued even further down. You could end up with a model that's really large and potentially unwieldy. So it's important to keep in mind that decision trees have this sort of exponential growth to them where every level can have twice as many decision points as the level above it. So if you don't put controls on the depth of the model, you can end up making something that is perhaps bigger and more complicated than you really want to. So to wrap up, decision trees are a fairly easy to interpret, yet surprisingly expressive form of predictive model. A decision tree of limited depth can provide a good starting point for classification, and the model complexity is easily adjustable. Now in the next lesson, and the final lesson of this series, we're going to learn about random forest models, which are an extension of decision trees that tend to perform a bit better than decision trees and can do pretty well on a wide variety of both classification and regression tasks. So thanks for watching, and I'll see you again next time.